I'm Xiao. Daniel and I will give a deep dive talk about the new features in Spark 3.2 and Spark 3.3. And all of us are part of the Spark group in Databricks. Daniel is a tech lead of our SQL team, and Wenchen and I are Spark PMC and committers. Databricks is a data and AI company. We are the original creators of the Spark data lake and ML flow. We provide the first lakehouse, and which offers one simple platform to unify all of your data, analytics, and AI workloads. We are working with over 5,000 companies over the global. At first, let me share some exciting news about our Spark community. Maybe you watch the keynotes. We are very proud we won the Signal System Award this year. It's a big deal. Signal is a top conference for both researchers and engineers. The award is given annually to one significant system whose technical contribution have had a significant impact on both theory and the practice of large-scale data management systems. And this year, our Apache Spark won this award because of its innovation and the huge impact on both industry and academia. It's amazing. And also, after 13 years, the growth of the Spark is still very fast. Spark has been downloaded 45 million last month. And this month, the number is even higher. This only counts the PyPy and the Maven Central. And the report, this represents like a 90% year-over-year growth in downloads. PySpark alone is being used at least 204 countries and regions based on the PyPy downloads. PySpark has become the top one distributed data processing system in the Python community. And in this map, still some countries are still white. They will be our next target. And also, Spark ranked the top paying technology in the Stack Overflow 2022 developer survey. And based on the hacker rank and the Stack Overflow, Spark developers should see 30% annual salary increase in the last 2 years. If you did not get this increase, you should first learn Spark and talk with your manager and show this report to them. And the SQL and the Python are the third and the fourth most popular language in Stack Overflow developer survey. Maybe Spark can support more language like JavaScript in the future after we implement the Spark Connect. Spark Connect is a big achievement direction that Daniel will introduce later. In Databricks, SQL and Python are the top two language in the interactive workloads. So SQL and Python have been the major focus of our Spark community in the last 2 years. Today, we are focused on the two release, Spark 3.3 and Spark 3.2. You can see there are a lot of new features we shipped in these two releases. Like what I just mentioned, we are focused on, the community in the last two releases deliver so many features in both Python and the SQL. And these two releases resolve more than 3,300 JIRAs. And At the same time, we also improve the performance, increase the stability, increase usability and extension. In today's talk, I will first cover the Python, ANSI SQL, and the environment. In the second half, Daniel will introduce the major features in performance, streaming, extensions, and the many cool features and the future roadmap. First, Project Zen, Python. Project Zen is a project we started 2 years ago. It focuses on the improvement of Python usability. It targets better error reporting, Pandas API support, and the performance improvement, and the Pythonic API design. In last year, the community decided to bring the koalas into Spark. And since Spark 3.2, all the Spark users can use both Spark API and the Pandas API to process your data. And this will simplify the migration from the Pandas to Spark. And this Pandas API also can benefit the PySpark users because they support many tasks that are difficult to do with Spark. For example, plotting the data directly from the PySpark data. In 3.2, you can just easily call this API and plotting your data. And today, I will also introduce some Pandas API, like a merge as of. It's very useful for your regular data processing use case. Yeah, I will give you some examples. Today, it is a good time to show the achievements we made in the last 2 years. Since announcement of Project Zen, summer, May 2020, the adoption of PySpark is a 5 times increase based on the PyPy downloads in the last 24 months. It's a huge increase. And this month, June, we saw the numbers much higher, 23 million. And the Pandas API on Spark can achieve better performance in both single-node machine and multi-node clusters. Like a SQL and the data from API. Pandas API are also optimized by the same Catalyst optimizer, adaptive planning, and the whole stage code execution engine. So you would get more or less the same performance regarding of which one you use, no matter data from PySpark or Scala data from, similar. All of them are just API. And now, Spark exposed different API for different use cases. We hope you all find the addition of the Pandas API to Spark makes you move to the big data, Python data science simple. After we have Spark Connect, we can support more language API easily. In the last 2 releases, the performance of the Pandas API is further improved by the latest progress in our engine, including some Bloom filter join, enhancement in the query optimizer, we turn on the AQE adaptive query execution on by default, and many the coverage improvement of a whole stage code generation. And also data source enhancement, we just announced Delta 2.0, and also Apple contributed their package reader. It makes the complex type reading much faster. And all this improvement in Spark will also benefit our Pandas API at the same time. And this clearly shows the advantage of Spark. We are a unified engine for data analytics, data engineering, and the data science. In the PySpark, in the Pandas API on Spark, we also made some good movement. We switch the default index from the sequence index to the distributed sequence index. The performance is around 2 times faster for 5 GB tables in a distributed environment. More importantly, we continue to improve the coverage of the Pandas API. Currently, our target is to make the Pandas API compatible with the latest version of Pandas. In Spark 3.3, the corresponding Pandas version is 1.3. In Spark 3.3, we added a new doc. It lists all the supported API. You can easily find out which API or which parameters are supported. And after porting the koalas into Spark, Spark 3.3 implemented more Pandas API and parameters. So today's talk, I will majorly focus on 2 API. The first is merge as of and time delta. SF join is very popular and powerful. It's to join the records that might not have exact match. It is like an ordered left join that can match on the nearest key rather than the equal key. You can decide the direction, backward, forward, or nearest. You also can narrow the search space by specifying the equivalent keys with parameter by. This is like what Pandas provides. And then let me give you an example. Here we want to do an SF join of df1 with df2. The join is on the column B. So the row selected from the right table is the last row whose B value is less than or equal to the B value in the left table. And the second row, A2 in the left table is matched with the third row, C4 in the right table. And 4 is the closest value in the right table that is still less than or equal to 5. Yeah, that's the result. Now, let us specify the by column ID. For the first row of the left table, there are no matches in the right table, so it will return the first row. But the value of column C is the result is none. And the parameter by is to specify column name or list of column names matches on these columns before performing the merge operation. So merge as of join is natively implemented in the Spark query engine. It is automatically converted to a scalar subquery like this. And so far, we don't have a SQL API. If you want to use this feature, you can just call this Pandas API. Time delta is another critical feature for the Python users. And time delta is a class of a datetime module in Python. It is like the datetime interval data type of a standard SQL. It represents a duration expressing the difference between 2 days, time or daytime. In Spark 3.3, time delta can be used in any PySpark API. For example, in the new feature, merge as of join, you can use the time delta value to specify the tolerance within the range. For example, after we specify the tolerance, so there are no match in the right table for the last row of the left table because the difference between 2020 130 and 2021 second is bigger than 1 day. Yeah, as we just discussed, we are still implementing more and more Pandas API. So this here is a list of API that have been implemented in our master branch, but not released yet. So it will be available in the next release. And to the existing Pandas users, Pandas API on Spark can be used as a drop-in replacement for Pandas. Especially when your data volume keeps growing, you might face a big data challenge later. Pandas user can also take advantage of the benefit of a PySpark with minimal efforts, so get to the value much faster. Even if your data volume might not be big enough, might not need a distributed computing engine, you can still use a PySpark to support the streaming use case for each batch API, or to integrate with the whole Spark ecosystem. For example, data lake, ML flow. Of course, you can query data using the SQL language, easy. So I will introduce a new feature we added in 3.3, like a Python standard string formatter in SQL. Yeah, so this is an example. We added a built-in string formatting operation in Spark 3.3, and it provides ability to do complex variable substitution and value formatting. In this example, we replace TBL by my date frame. And here, the select clause lists 3 different ways to specify the column ID of my DF. Just a very cool usability feature. And also in Spark 3.3, we inline the type hints. So we can achieve better auto completion. For example, in Databricks notebook, if you type tab, you can see the parameter type. You can see the difference between 3.2 and 3.3. You can see the similar difference if you use other notebook like Jupyter. Yeah. And after inlining the type, we can generate better documentation. In Databricks notebook, if you type shift and a tab, you can see the document with both parameter type and the return type. We heard many complaints about how difficult, how hard to debug our Pandas UDF or Python UDF. So yeah, especially performance issue. So now in this release, 3.3, we introduced a Python Pandas UDF profiler. It provides a deterministic profiling of your Python UDF. And the generated contains a set of useful statistics that describes how often and for how long various parts of the program executed. And the profiler is very useful if your Pandas UDF contains very complex and expensive business logics. For example, calling some external library. Yeah. So this is just an example. You can see the sleep, we sleep 1 second, and after the profile shows clearly the total time is 10 seconds. We have 10 calls, each call maybe just 1 second. Yeah. Okay. ANSI SQL compliance is another major initiative we started 2 years ago by Matei that was introduced in Matei's keynotes. Finally, the ANSI mode was a GA in this release. So in the future release, we will continue to add more standard SQL features to Spark SQL and make simpler your migration from the other SQL system. Today, I will introduce 2 SQL features and then focus on what we changed when ANSI is enabled. Lateral subqueries. A query prefixed by the lateral can reference a column exposed by a preceding from item in the same from clause. So such a construct is called correlated or dependent query. So in this example, you can see the lateral subquery, the where clause tab1.id reference to the external table. And the lateral subquery can also be used to simplify your queries, just like the CTE, make it more straightforward and even more efficient. For example, in this example, you can reuse the common expression A1 plus A2, B1 plus B2, instead of just copying and pasting them in the whole queries. Yeah, CT can do the same thing, but in more complex way. Before Spark 3.2, Spark interval value cannot be compared with any other interval values or persisted to the storage. So since 3.2, we re-implemented the interval type. So it represents intervals of the time on a scale of the seconds or months. So there are two types of interval, daytime interval and year-month interval. And you cannot combine or compare year, month, and daytime intervals. Now here we listed like multiple examples how to use interval type, and you can compare the date difference with interval values. Starting from Spark 3.3, ANSI mode is ready for production after 2-year development. You can turn on ANSI mode by setting flag spark.sql.ansi.enable to true. And ANSI mode follows a SQL standard in how it will deal with certain arithmetic operations and the type conversions, similar to most of database and the data warehouse. And enable ANSI mode, it can improve your data quality, integrity, and portability. Make integration with the BI and the partner tools simpler. So here I list the major difference between the ANSI mode and the non-ANSI mode. In non-ANSI mode, arithmetic operations performed on numeric type may return the overflowed value or null. So where in ANSI mode, such operation return an error. Yeah, you can see divide by 0. Yeah, this is, you will return a runtime error in ANSI mode, but in non-ANSI mode, it just return null. The behavior of some built-in function can be different under ANSI mode versus non-ANSI mode under specific conditions. For example, ABS native 128Y. Y means the data type tiny int. So the range of tiny int number is from negative 128 to 127. And this is, this number 128, when you, the ANSI mode is false, so it returned negative 128Y, right? So this is an illegal tiny int value. In ANSI mode, it just, return a runtime exception. And here we listed 14 built-in functions that have a different behavior when you turn on ANSI. Yeah, you can see the difference easily. And the rules and the behavior regarding the trust are stricter in ANSI mode. They can be divided into the following 3 categories, like compile time conversion rules, runtime errors, implicit type correction rules. For example, if you try to cast a Boolean type to a timestamp, you will get an exception at the compile time, and instead of just 1 second after epic time. This is wrong results. And for example, if you try to cast a literal A to integer, so you will get a runtime exception instead of null. To avoid the runtime error in ANSI mode, you can use a try cast for null on error behavior. So in this release, we also added the other try function Daniel will introduce later. The last major ANSI changes are made on implicit type correction. Non-ANSI mode is based on a set of inconsistent rules that was introduced for following the hive behaviors. And the ANSI mode is determined by the type precedence and the least common type resolution. When ANSI mode is on, we use this type precedence graph to define whether values of a given data type can be promoted to another data type implicitly. And the special rules apply for the string type and the untyped null. A null can be promoted to any other values, while a string can be promoted to any simple data type. Here is another typical example to show the implicit type correction rules work in non-ANSI mode, but fair in the ANSI mode. When you use a non-ANSI mode, 5 equals to string 5.1 will return true. But the result does not make sense in most cases, right? So when using ANSI mode, it will show a Spark number format exception and tell you, okay, the value 5.1 of the type string cannot be cast to bit int, and because it is mere form. Okay, today I would suggest to all the Spark SQL users to upgrade your Spark to Spark 3.3 and turn on ANSI mode in your Spark application for better data quality, integrity, and portability. Arrow Framework is one of the most impactful projects we are working on. And our community keeps complaining about the misleading error message that contains a very long Java exception dump. And the message quality is poor in many cases. So we are building a new error framework and trying to migrate all the error message to the new framework. The new error should be actionable, stable, and well documented. So the new error should be, this is, here I just give some examples. So let's maybe divide by 0 is yes. I will use this as an example. You can understand how useful the big difference. First, each error message corresponds to an error class with a corresponding parameter. And the second, it should also contain the detailed description and explain what happened. And third, we need to tell users how they can fix that. And we provide more examples for each error class. The new error framework is amazing, but that also requires a huge effort to migrate all the error message to the new one, and then improve the error message and improve the documentation. But we believe this is significant for the whole Spark community to improve our usability and make Spark simple to use. Besides error message documentation we just presented, we also did the other amazing things in documentation and environments. Like last October, we finally created a brand new homepage for the Spark. And the new homepage clearly shows our vision, mission, and the latest progress. And the Spark is a unified engine for data processing, data engineers, data science, machine learning. We can run the Spark on your laptop cluster with hundreds or thousands of nodes. In the future, after we finish the Spark Connect, we can even run Spark on edge devices like your mobile phone. And also, starting from the Spark 3.3, we also introduced a new API reference dot for the Spark R. And after porting the koalas into Spark, now the API reference dot for the Pandas API on Spark is also available. And more importantly, we finally created our official Docker image in the Docker Hub. You can easily download Spark image and play it in your laptop with an actual setup. Only 2 commands are enough. Then you can use a SQL API or Scala or Java API to try the latest features. Of course, you can do the same thing for the PySpark by just download from PyPy. Only 1 command. So there are many critical environment updates. We finally upgrade our Log4j to Log4j 2. And Java 17 and Scala 2.13 support are in beta preview. And also thanks to the contribution by the engineer from Apple, so we can successfully run the Spark on the powerful machine made by Apple. Okay, Yeah, so Daniel, my teammates will present the second part. Thank you.
Hello, my name is Daniel. Thank you, Xiao, for presenting the first half. That was very interesting. And we'll move on to talk about new performance and other features in Apache Spark 3.2 and 3.3. We'll start with performance. There's a lot of interesting topics to cover. Thank you for your attention, and let's dive in. So let's begin with runtime filtering. With features in this area, we can speed up queries significantly by reducing future work to be done at the shuffle boundaries. As we can see, these improvements make a big difference, as shown in TPC-DS queries over both delta-like tables and raw Parquet file sets. To understand this problem, let's consider this type of sort merge join between two tables. Shows up frequently in Apache Spark execution plans. We have a full scan from one table preceding a filter before reaching the shuffle boundary on the right side, at which point the Spark executor performs a full sort and stages all the contents to disk. Likewise, in the separate stage, a full scan from the other table feeds into another full sort plus staging to disk. Finally, the sort merge join operator in the third stage consumes both sorted contents and merges them together in order to proceed onwards with a query execution. This pattern is problematic. The tables are large because sorting and shuffling this much is expensive. Spark now supports performance improvements to address this use case. We can update large join inputs like this by adding Boolean filters to allied rows, saving later shuffle and sorting cost. Each new Bloom filter uses a scalar subquery to apply predicates over the join keys shared between the two tables. This works for both shuffle hash joins and sort merge joins. As a result, shuffle costs are reduced significantly, along with end-to-end runtime and resource usage. You might be wondering, how is this different from dynamic partition pruning, if you're familiar with this? There's some similarities. The differences are that Bloom filter joins only work if we can push filters down through the shuffle boundary, and does not reduce table scan IO because we scan the other table to produce the Bloom filters on the other side. However, it works for any join keys over large tables, even over non-partition columns. Right, so looking at a brief example, let's look at how Bloom filter joins make queries faster. So here we have two relations, R and S, and a query that joins them. Normally, we might add a sort merge join and shuffle both sides. We add Bloom filters, and we can look at the execution plan again. Here we find a predicate has been added above the scan of R, where R can be a table or any relation, any table subquery. The predicate has this may contain expression to implement the Bloom filter, referring to the hash of the join key column. In this way, we significantly reduce the number of rows scanned from R that eventually reach the shuffle boundary. So looking at another example, let's look at this TPC-DS query number 32. This query requests a join between three tables: catalog sales, item, and date dem. Pretty simple, except until we get to the where clause, super complicated, a lot of conjuncts. There's even a scalar subquery in there. So let's see what happens when we plan it. And we run this query with Spark 3.3 and look at the Spark UI to see what's going on. We see the new Bloom filter, and we find it's reduced the rows generated by the preceding table scan from 123.6 million down to 46,000 rows. Okay, so that's a huge difference because everything that comes out is going to disk for the shuffle. Okay, so in general, since Spark 3.2, adaptive query execution is enabled by default. What this means is adaptive query execution, this is a powerful platform in Apache Spark where in each shuffle operation collects detailed statistics at the shuffle boundary and then reinvokes the optimizer for the following stages. This is actually running the logical planner in essentially the same way as when the query originally arrives at the driver. This empowers the query planning to run using the exact knowledge of intermediate cardinality, statistics, data, rather than planning time estimates, which if you work in databases, you realize how bad they can get pretty quick once you get out of the table scans. As a result, Catalyst now can confidently make plan decisions that seemed too risky before. We can switch sort merge joins to broadcast hash joins, for example. This has a dramatic difference. For example, if the right side table is small, you do broadcast hash join, and it's a significant difference. There's other features. Dynamic partition pruning, I'll go over next. We can eliminate limits. We can optimize away one-row query plans. Some of these are very frequent, and some of them showed up in someone's use case and they cared about it, so they sent a fix, and now it's fixed in Spark. So let's go over these. Dynamic partition pruning, the problem is kind of similar to the problem that we went over with Bloom filters, where we have a huge join and it's slow. So the idea is we can propagate filters to the target stage from the right side of the join with the filter. We send information over so that we skip partition scans from the left side, partition prunings. This is very powerful because we can significantly scan less data. Not only do we shuffle less, but we also scan less. Okay. For another optimization, we can think about this problem. We're scanning tables. We do a shuffle, maybe for an aggregation or a join, and we end up with a lot of small files. Maybe 5,000 files. This is bad because there's a fixed overhead with opening each small file, and this can slow everything down. For folks who went to the Delta Lake talks, you might have heard there's optimized commands to fix this and kind of compact them together. In Apache Spark, we use adaptive query execution to merge these partitions together, and the following stages execute much more efficiently. Okay. As another example, you could have a skewed joins where you're joining two tables, but there's a lot of rows from the same key on both sides. Maybe it's a hotkey. Maybe half the rows on each side have the same join key or something, and then they all get sent to the same worker, and it just gets super slow. We now detect this, and we perform a split shuffle read to compensate for this. We detect the hotkeys, and as a result, the stragglers are mitigated, and we can reduce end-to-end runtime much more than we could previously. So here's a blog post. There's a lot more information on here. Please feel free to check it out. Lots of interesting stuff here. Cool. Okay, so next performance feature that's interesting. Spark has implemented a new execution model called whole stage code generation. It's inspired by the Hyper code gen paper from Thomas Newman. The idea is we're fusing strings of operators together, up to including the entire stage into one whole stage code gen node, running the generated code of these operators. So not only do we generate code for each expression, but each operator generate a bunch of Java, compile it, and run the whole thing in one block. Right? So we end up with a general purpose execution engine, just like the Volcano iterator model, kind of row by row traditional model, but without all the performance downsides. Because the generated code, as we see on the right side, we're avoiding all these virtual function calls saying expression.eval or operator.getNextRow, and then it does a virtual function call and says, what operator is this? And now it's just running Java, and the Java does a loop, and it can do compiler optimizations, loop unrolling, cool stuff like that. SIMD, we can put data in registers. Basically, all the fancy stuff that compilers are good at doing. The Apache Spark community has improved the coverage of whole stage code gen. We now include sort-based aggregates without grouping, full outer joins, and many, many more cases. This improves query performance with no user visible changes in the result. So here's a kind of detailed example of an expression that generates code. This is kind of a simple example. It implements the Bloom filter we mentioned previously, and most of the machinery moving parts involved in this example were binding Scala objects with names that they can be visible from Java. But in the end, this method runs and generates Java, and then it's suitable for compiling into the whole stage code gen block for that stage. Cool. So moving on a little bit from execution, we've looked at the SQL compiler and the planning process. And we've made a bunch of, the community has made a bunch of steps to improve the compiler performance. So during this process, each original query, originally expressed in SQL or data frames, parses into an unresolved logical plan. We see it in this diagram Xiao showed in a previous slide. So I show the diagram again. We transform it through intermediate data structures into a final sequence of execution stages. We use the transformations use rewrite rules. Each one traverses the tree, traverses the plan for one specific purpose, either a single time traversal or repeatedly until the plan stops changing. We call this fixed point. Since each rule is designed for one purpose specifically, and the query plans are immutable, each rule generally builds a new plan by copying subtrees. Right? So you traverse the tree, you reach a node you'd like to modify, you create a copy of it, and you assign subplans to the children. Right? So the query optimization logic becomes very clear and maintainable, even with many, many rules. You can have hundreds of rules. It's really nice in the debugger. You can be stepping through in the debugger. All of your previous plan trees are still valid variables. You can say, like, what's the previous tree? What's the next tree? You can type stuff and try to evaluate this rule and see what happens. So to speed this up, in Apache Spark 3.2 and 3.3, we've done many things with the community. Some specific examples, we've added frameworks to prune entire subtrees from the traversal process using bitmaps to check for node presence in O of 1. Right? So you can be considering a subtree, considering a logical plan, and think, should I run this rule? And we have a simple check, this transform up with pruning check. Says, does this subtree contain any projection or any window functions? It does the check in O of 1 because the bitmap is just stored in every node and propagated up. Right? So this is very fast, and you can just skip the whole traversal if the rule doesn't care. Okay, so copying, when we do want to change the plan, Copying nodes becomes much cheaper. A bunch of detailed analysis went into this. We combined a bunch of rules for type coercions into one. These rules are related, and instead of doing n traversals, we can just traverse once and then check each of the nodes each of the rules conditions at each node. By the same token, when we do want to change the plan, we have options about how to actually do that. We found there's generic logic that we say copy this node with new children, which is very frequent. We have a node, say I want to assign 2 new children, and this is super frequent, right? So we looked at it, and we found most nodes have 1, 2, or 3 children max. I mean, some have many, but the vast majority are in these cases. So writing separate logic for these cases speeds up this copy with new children or map children operation significantly. We see it in the TP-CDS queries. The compiler time drops a lot because we're simply doing fewer lists, Scala collection operations. Right? So it reduces latency a lot. Right? So there's many more optimizations, but can move on to other topics. Right? So stepping back a bit, moving from performance to features, we've added a bunch of new features in Apache Spark 3.2, 3.3. The community's done a lot. So with data frames in SQL, Apache Spark provides many ways for data scientists to work and unlock insights. We're excited to announce just a subset of these, the frequently asked for by users. Please keep in mind there's a lot more, a lot more than this, but we have limited time, so this is just a subset. We can start with 43 new built-in functions, including tools. There's a lot of interesting stuff in here in Spark 3.2, 3.3. We've added tools to compute histograms and quantiles, perform operations and ETL jobs without raising errors, such as the try-cast example Xiao mentioned, which helps make ANSI mode more usable. Lots of different categories. There's even more functions in the pipeline as we speak now, so there's more coming. And these units of computation, we can use them in the SQL APIs and the data frame APIs. Right, so going through a few examples quickly, there's this two-number function. It takes a string input and a format string, and it uses the format string to parse out the input into a number, to a decimal. And this can be useful for data lakes where you have a bunch of strings. For some reason, the data's been encoded as strings, and that's how it got there, and you want to parse it out into numbers. It's pretty flexible. You can configure like where the decimal point can be or how many digits it can be. You can add padding and stuff like that. So this is in many data warehouses as well, so it should make porting stuff easier. We have this contains function to check if a string is in another string. It's like a regex check, but it's faster and easier to understand, and the optimizer understands it more natively. There's encryption support. So there's AES encrypt and AES decrypt functions. We support custom encryption using the AES algorithm. So we have key lengths 16, 24, and 32 bits. And this is kind of a good approach, doing encryption with open source code. This replacing the security through obscurity model, right, by saying this is open source code and this is how I'm doing my logic, and it makes us actually audit the code instead. Just make sure don't open source the keys, just the code. We have a bunch of functions to work with structs, maps, and arrays. These are really helpful for nested data and they're supported in ANSI SQL. So this map contains key function will let you check for the presence of a key. There's this histogram numeric function. So you can do a histogram. You give it a certain number of bins. It gives you an array of pairs. And the pairs represent the centers of the bins. Right? So these functions for histograms and quantiles are really useful for just cranking through a bunch of data and trying to make decisions, right? Like look at the quantiles of all these data points and see like how does the data group up? You know, is there a spike somewhere, or what am I looking at? Okay. So moving on from functions, we have introduced this hidden file metadata column. So this is a new feature where you do a select star from a table. It will not reveal this information, but you can name it explicitly and return information about the files you're scanning. So you can say _metadata.file path, and it'll give you a column with the file path of that file, or the file name, or the last modified time, right? And this is kind of very flexible. So there's use cases like you dump out your files and then you put them in a directory structure with the year and the month and the date in the file path. And that's kind of a common thing to do. And then you can, in SQL, you can query all that out and then parse out the date from the file name, right? So that's just a common use case, but there's lots of things you can do. But I should mention, if you're gonna try to query at timestamps, use Delta Lake. Don't do that, but you can do that. Yeah, Delta Lake's much stronger at time travel and querying at specific timestamps. Cool. So here's an example. Create 2 CSV files. And cat the files. There's some data, and that's the contents. And then when we can query it with Spark, we create data frames, load up the files, and then select the metadata contents. And we end up with columns for the file path, file size, and file modification time. And you can combine these with anything, right? So you can count things and sum things and group by the file path, right? So you can sum up all the data in each file and group by the path, and then if your path, if you have 1 day of logs or whatever per file name, then you can do that. Or you can filter small files out, stuff like that. Cool. So moving on again. So now I'm going to switch gears a little bit, talk about Spark structured streaming. Right? So Spark structured streaming jobs, it's a powerful way of using Apache Spark. And you can use window definitions, essentially. And you control how much data that Spark will process within each session. Leave the application online, define your session, and then you'll get outputs depending on your session definition, right? So, for example, tumbling windows are pretty simple. You give a fixed duration, and then it'll do a session of that duration, 10 minutes, then the next 10 minutes, et cetera. Sliding windows are kind of an extension of that, where the windows are still a fixed duration, but you can start a new one before the previous is finished, so they can overlap. We now introduce session windows, so this is new, right? And with this new feature, the windows are not fixed duration anymore, but you can define the windows based on events, right? So the window can extend until a time period in which no events take place. So it can be variable length, like you just define the session until activity stops, and then the session is over. The next window begins when the next event takes place, right? So you can have short sessions and long sessions. And this often matches what folks are looking for, right, when we're sessionizing data in a streaming fashion. Cool. So when we're running structured streaming jobs, you define the semantics with the triggers. And the trigger basically defines when to perform updates and how large the batches should be. These generally operate while the Spark instance remains online, except in the case of the one-time micro batch trigger, which runs in a one-off mode, and you can avoid keeping the application online. You just run the one-off trigger, the one-time micro batch trigger, and it'll gather up all the changes from the last invocation and crank through it in one go. Right? So this is really convenient to avoid keeping the application online for a long time, but it can be a problem if there's a ton of data and you bring it all into memory. Right? You can the consumer, and then everything is terrible, and it crashes and it's bad, right? So to fix this, we're introducing this available now trigger in the community, which fixes this problem. It's retaining all the benefits of the one-time approach, right? So you can invoke it without the application being online the whole time, but it splits the new data into micro batches for consumption by the user. So it fits within memory, but it keeps operating as needed, right? So it's kind of the best of both worlds. Right, so as the structured streaming job runs, we consider this state store, and it makes operators more powerful by letting them keep information that persists between runs, right? Persists between execution. We're announcing here, there's a new design using RocksDB, which removes all the limits from how much state each operator can store and retrieve, right? So it's possible to write unlimited amounts of data, and it's also possible to look up all of the state, or just a range of it. You can do a range scan, right? So if you dump out a lot of state and it's inefficient to read the whole thing back, you can get subsets of it back. We're excited about this. We're excited about the future potential for this to make stateful pipelines better and make streaming more flexible. Cool. So as an example, here's how to do a session window. And it's pretty simple, right? So a Spark streaming job doesn't have to be super complicated. It can just be a relatively simple definition, and then you just run it, and then you can evolve it from there. And API can look very similar to just a batch query, but it can just give you streaming updates, which is kind of cool. Cool. Okay. So we've talked about performance. We've talked about new features. Let's move on to extensions. Right. So one of Apache Spark's strengths is it can scan from many heterogeneous data sources depending on what we want to do. Right. It's absolutely essential for these scans to run efficiently if we're running on huge data lakes. So Apache Spark 3.2 and 3.3, we introduced many new performance features for scanning very popular formats like Apache Parquet and Orc, as well as new data sources you might define for your own needs. For example, using the V2 data source API. And of course, integration with Delta Lake has become even stronger this year, as we learned from other talks in this summit. Right, so let's look into data source V2. This launched recently. It provides unified interfaces for many data sources and serves as a platform for building new ones. Right? The kind of idea was to put a lot of effort up front and define these APIs, and then over time they'll bear fruit. And we find that they do. Today, we find they bear fruit with aggregate pushdown, as well as many other performance features, right? So with aggregate pushdown, you can generically define the data source's ability to absorb an aggregate on top of the table into the data source, right? So if you, for example, if you say count, select count from my Parquet file set, or whatever file set. You can remove the aggregate node and the stage boundary from the Spark plan and implement the count by just reading metadata instead, if you already store that in the file headers or columnar encodings or anywhere the data source might be able to give that to you for free. There's other new features. There's read and write metrics, dynamic filtering. There's storage partition joins APIs. These are really helpful to give metadata to the planner. So you can say, my data source gives you rows clustered by the first 2 columns, right? And then you do a group by A, select the group by the first 2 columns. You don't actually need to shuffle at all, right? Because the data is already clustered such that all the rows with every unique combination of values from those clustering columns are in the same worker, right? So that's really nice, right? By the same token, you can do ordering properties, so you can elide the order by if the data already comes out in that order, or you can merge join cheaper. You can do co-partition hash joins if you're joining the join keys, the clustering keys. Right? So that's kind of nice. You can avoid the shuffle there. This works with data frames, right, as well as SQL. And this kind of matches up with how a lot of these data sources work. Oftentimes, you'll dump out logs in ascending order of timestamp or something, or each file will have 1 day, or each directory will have 1 day of logs or something. And so just exporting it is helpful for optimizing. We also have group-based row-level operations, right? So what this means is you can do DML commands, and the DML commands can know the difference between being able to do updates with deltas in the data source or by replacing partitions, right? So most data sources fall into one of these 2 categories, where it's either a partition that if you want to do an update or a delete or anything, you wipe the whole thing out and write it back. Or you can do explicit deltas, and you do your updates, and you append the delta into the data source, and then you can define the difference between these 2 capabilities explicitly in the API. A lot more push down, a lot more interesting stuff. So we have top-end push down, sample and limit push down, partial and complete aggregate push down. These help with performance a lot. And so when we think about these operations, and you work with them for a while, you realize you can define a push down capability, but in practice, it doesn't trigger often sometimes, because you did an allow list of expressions that are supported because it was expedient, right? When you're implementing, you find, oh, it's not triggering, right? So the way to fix this is you implement kind of a general framework to represent the expressions or the aggregate functions, right? And this is emerged in the data source v2 API, and it helps represent pushdowns in many more cases. Cool. Okay, so moving on past data source v2 user-defined data sources into core scans, Parquet. This is Apache Parquet. It's a flexible and powerful columnar encoding. It's based off of the Google's Dremel paper, right? So you can do structured data, nested structures, and it supports that. It's very flexible, so there's different encodings. It's showing up everywhere. It's showing up in data lakes, in just giant file collections in S3. It's showing up in Delta Lake. Delta Lake, it underpins the storage. And Apache Spark has deep integration with Parquet. It supports high-performance scans. So new features, there's column indexes. In the Parquet vectorized reader, Xiao announced that is launching, and contributed by Apple, right? And then we can now push down min, max, and count aggregates into Parquet itself. Like I mentioned, That's really nice when these are really common aggregates and you can just get the data out of the metadata, the headers. And then you do that all the time and you don't have to like do a big shuffle. We're especially proud to talk about complex types. Complex types now work. So you can select a struct, you can select arrays, tons of performance improvements in these cases, right? So Parquet, the protocol and the code, the Apache code itself, will let you specify, I want these subfields, right? So you're scanning this array or these subfields of this array or this struct with only these fields. You can tell Parquet you want these things. And this is now supported in the vectorized reader. So this is great for flexibility. You can define Parquet columns of these types and then populate them and then select them out with ANSI SQL or data frames. We're actually looking at our own internal observability frameworks at Databricks to look into using Parquet files with these nested structures. And there's some initial promising results with ANSI SQL support, and you can just query structs, query fields within. And we can use field pruning capabilities by Parquet. So yeah, the other major format is Apache Orc. And we're proud to announce forced positional evolution and nested columns in the Orc vectorized reader as well. Aggregate pushdown as well, right? So efficiency and flexibility improve. And there's a lot of different use cases, so we're proud to announce these improvements. Cool. So we've talked about user-defined V2 data sources. We've talked about core kind of frequent Apache columnar encodings. Let's talk about a really important data source. Let's talk about Delta Lake, right? For extensibility and extensions, Delta Lake is very important for the lakehouse. It's the foundation of the lakehouse. Michael Armbrust described in the summit, data warehouses were originally born to support storage and query with SQL, but they're limited, right? You can only get so big, and we have way more data than that. So then data lakes are born. And data lakes are just huge volumes that we store in the cloud, store in S3, store in ADLS, and then in open formats, but they're limited because you don't have all these performance features that the vendors have added to their warehouses, right? And you don't have query features. We're super proud to bring the best of these two worlds together in the lakehouse, right? So we have one roof, and we have the technology in Delta Lake enables the lakehouse to serve both of those needs at the same time. We have the reliability and performance of a warehouse, the scale of a data lake. These are open formats, open standards. You're not locked in at all. Spark can query efficiently from your Delta Lake, but it also has connectors for like every other system, right? So you can query it out with anything. You don't have to copy. You don't have to export it out, make a copy to Parquet. You can just query it. There's a strong open source community backing this, right? So it's there's also a lot of powerful features. Delta Lake 2.0 is coming out. So there's a lot of flexibility. Delta Lake 2.0, there's many performance features that we've talked about. Just in time for its birthday party today, Delta Lake's birthday. For example, we can organize writes into partitions, optimize for future scans across multiple dimensions. We can rename columns super fast with just metadata-only operations. We don't have to do a big backfill. And this is just the beginning, right? This is just the beginning of the features that are going to go into this from the community. So I'll go over a few of these kind of in the context of Sparks as a Apache Spark extension support. There's a little overlap with the Delta Lake talks as well. So a really interesting one is called generated columns, where you can simplify your life by defining a column is generated, and it can refer to previous columns, right? So in this example, you say, create a table with an event time at a timestamp, and the event date is generated from the timestamp cast to the date. You don't have to think about it. You don't have to write it explicitly in inserts or DML, but you can select it back. It's really easy to use, and it's very useful. Right, so there's a ton of performance features. As we talked about earlier, small files are the death of shuffles and performance because there's all these per file overhead that adds up. Delta Lake does a great job at solving this problem with compaction, right? So you can take the files and then optimize them, and then you can do that by itself, or you can do that at the same time as other operations. Right, so that's great. We originally thought this is only possible for scanning all the files in a data lake, right? And you just do it thousands of workers or hundreds of workers, and you just crank through it, right? And we kind of took that as a given before. Delta Lake lets you move on from that by allowing data skipping, partition file skipping, right? So we can put statistics and per file statistics in the files like min and max values. And then we can leverage that when we're querying. We take the filters or constraints that apply to the scan and skip a bunch of files, right? Yeah. So we've skipped files based on the min-max constraints, and we've sped up the query, we've reduced resource usage, and everything is awesome. Cool. Okay, so beyond min-max values, Delta's defined sophisticated feature called z-ordering, which boils down to clustering data among multiple column dimensions using something called space-filling curves. And what this means is you can do your z-ordering optimize command, pick the columns of interest in your Delta table, z-order by them, and then queries against those columns will be able to take advantage of the optimization. You can do file skipping, and it's not just one dimension. You can't say, what's the column I want to sort by? You can pick multiple, right? So this is a really, really big speed ups you get from this. Pretty cool. One more feature, there's change data feeds, right? So this is commonly associated with traditional database management systems or data warehouses where you get a pub/sub kind of channel type of thing for when the changes happen to your system, and you can subscribe to that. So you could think naively, oh, I could just pull the table and see what's changed, right? But this is kind of hard. How do you know what rows are different, right? How do you figure that out? You could kind of reverse engineer it if you try, but that's annoying, and it's slow, and it's error prone. So Delta Lake gives you a change data feed instead. It stores row level changes separately, so you can inspect only what you want, find the changes directly of interest, rather than looking in before and after copies, right? And Delta Lake manages this behind the scenes for you. So looking at some benchmarks, we're looking at kind of scanning a bunch of files, scanning a bunch of data in the lake with a baseline. And we find that using z-ordering compaction gives you an order of magnitude performance increase, right? And then we kind of compare to just compaction without z-ordering. It's still pretty significant improvement, right? Z-ordering gives you much better improvement, but both are beneficial, right? So you get data skipping, and you get all these performance features. Cool. So to summarize, Apache Spark 3.2 and 3.3 comes with many new performance and features, tools to unlock the power of your data in ways that you want, that make sense to you. It's an open source system that gives you the power that you need. The There's full SQL querying, including ANSI mode, which is new, to standardize logic, make it easier to move queries from other systems to Spark. For Python, Pandas is now merged into core Spark as PySpark with Pythonic error handling and useful UDF profiling tools. Very useful. There's structured streaming improvements like session windows, available now trigger in the RocksDB state stores. Lots of usability features and improvements, hidden file metadata, inline type hints, enhanced profiling. So we're super excited about these things, and we're excited to work with the community more as Spark grows, going more into the future as well. So that's the kind of the talk about what we've covered and what's happened till now. Switching to the right side of the curve, talking about the future a little bit. We learned about Spark Connect in the summit. This is a really interesting idea. And as Reynold mentioned in the keynote, this is going to be very powerful. We're defining a common API boundary. How clients can issue commands in the driver to the driver from other services, separate endpoints. This lets us use more programming languages and run Spark in more places. Martin's demo kind of showed Spark Connect to do analysis with data frames on an iPad. That's pretty cool. You don't have to be on a Spark driver anymore. So this will let you query huge data lakes and prototype quickly at the same time in the way that you've grown used to, but from anywhere. We're very excited about this. So briefly looking into how it works internally, the protocol will use gRPC and send unresolved logical plans from the client. So this is basically analogous to just a parse operation of the SQL. Serialize those, send them with gRPC to the Spark driver, and then return results back in Apache Arrow format. These are both open source frameworks. They've been heavily tuned over many years, right? So, for example, gRPC, a very modern library, it simplifies the client implementations. So if you're an end user and you want to use this, it's very simple. The framework gives you a lot of power. For example, there's native support for flow control, so you don't have to think about, am I getting too many replies and eat up my memory? Or am I going to get a callback when the stream is broken if there's a failure? You don't have to worry about that. The framework gives that to you. Great, so we can use SQL and data frames anywhere. We can seamlessly go back and forth between imperative client logic and big data with Spark on separate services with Spark Connect. Cool. So in addition to these benefits, we also get operational improvements too. We can independently upgrade Spark. You can leave the client and upgrade the servers. You can use step-through debuggers in the client. We can add observability. All these things help make Spark serve as the cornerstone for big data analysis everywhere. Great. So we want to take this time to give many thanks to the Spark community and the contributors over the entire world. Thank you all. Thank you very much for your sustained efforts and support in keeping the momentum alive.